Hi there. We are going to talk today about what's called the power of a hypothesis test. And so let's jump right in. But before we do, but when I think of something being powerful, I think that is like a good thing. And I think if you have that like positive kind of connotation to the word power, it might help you remember what the definition is. Because our goal ultimately, when we run a hypothesis test, my goal is that I want to prove, and remember we said we can't really ever prove, but we're trying to find evidence um, for the alternative hypothesis, right? When you hypothesize something, remember HO is what you like assume to be true, but then we're actually trying to prove HA. And we said the word prove, we're not actually proving, we're finding evidence for. So we talked about error, type 1 versus type 2 error. If we did not find convincing evidence for HA, we could make a type 2 error. The power of a test is if we know that HO is not true, if we know that a certain value of the population is true, how likely or what's the probability that we avoid a type 2 error when we do a hypothesis test? So I think it's easier to kind of think about this table that we've looked at. So remember, there's like a truth about the population, either HO is true or HA is true, and then we either reject or fail to reject HO. And so if we check this definition, let's think about this. The power of a test is the probability that the test will find convincing evidence for HA. So in other words, we will reject HO and find convincing evidence for HA when a specific alternative value of the parameter is true. So in other words, when HA is actually true. So the power of the test is really like this box here. Let's look at an example. Let's return to this battery example, right? So based on previous years of experience, the company's AAA batteries last for 30 hours of continuous use on average. The company is doing an SRS of 50 batteries, using them continuously till they're drained. Alpha is 0.05. Here's our HO and our HA. So we're trying to find evidence to say that the actual population mean time that these batteries last is more than 30 hours. Okay. So the new batteries are more expensive to produce, so that the company would like to know that they really do last longer. They want to prove or find evidence, right, that HA is actually true. So I'm telling you that the power of the test to detect that mu equals 31 hours is 0.762. In other words, what does this actually mean? It means it's a conditional. If the actual population mean lifetime of those batteries is actually 31 hours. So if that actual population mean, that population parameter value is actually 31 hours, there would be a 76.2% chance, or in other words, 0.762 probability, that the company would reject HO and that they would find evidence to say that the population mean is actually greater than 30. So there's going to be, one thing to clarify, there's going to be a different power value, like meaning the probability, for each possible value of mu. So in other words, this is the power of the test when mu is 31 hours. But if mu was actually 32 hours, the power value, that probability would be something different. I don't know what it would be, but it wouldn't be the same. Okay, so keeping in mind, it's a conditional. If the true mean is actually 31, right? So this is a conditional probability. This is the probability that we reject HO. In other words, find evidence to say that HA is true when the population mean actually is 31. That's the power of a test. So let's think about type 2 error here, right? Going back here, we now know that HA actually is true because we're now saying, well, I know, remember HO was that mu equals 30, HA was that mu is greater than 30, and so I now know that mu is greater than 30. I'm living just on this right-hand side of this table. HO can't be true because I know that HA is true. Do you follow? So we know that HA is true because this is a conditional. So the probability that I make the correct conclusion, given that HA is true, in other words, the power of the test, plus the probability of a type 2 error, given that HA is true, has to be equal to 1. Now notice, I'm not just saying the probability of a type 2 error. I'm just saying the probability of a type 2 error given that HA is true with that specific value. So let's go back here. The probability then that the company would make a type 2 error when we assume that the population mean is actually 31 would be 1 minus the power of the test, or in other words, 23%, 23.8%. So in other words, if the power of the test for a population mean value of 31 hours is 76%, then with that same population mean value, 31 hours, the probability of a type 2 error would be 0.238. But I just want to stress that this is the probability of the type 2 error given that the population mean value is 31. So again, it's when I condition on HA being true, right? Okay. All right, so obviously power is a good thing. We want, if HA is true, we want to reject HO, right? We want to make the right decision. So let's talk about how can we increase the power of the test, that probability, right? Therefore, decreasing the probability of making of a type 2 error. So there's a couple ways we can do this. And in order to kind of explain these things, I want to draw you a little picture, and I want you to think about this picture. So let's go back to the previous battery example. And let's think about HO was that mu is 30, HA was that mu is greater than 30, and we said that the actual mu was 31, right? Again, this is all assuming a specific actual population parameter value. All right, so when I do my hypothesis test, when I check my conditions and I do my hypothesis test, again, like ignoring this part right here. So I assume that HO is true. So my sampling distribution would be centered, my sampling distribution, I'm going to write this up here, sampling distribution would be centered at 30 hours, right? And this is what we assume to be true, right? We assume this to be true because that's what HO is. When in reality, this is the reality. So this is the assumption. And in red, I'll draw the reality. So in reality, this black normal distribution is actually not the sampling distribution for the mean. It would be centered at 31. So just think of this down here as a number line. This would be like 29, 29, 30. Here's like 31, 32. And I don't know what the standard deviation is, and it doesn't necessarily matter. But In reality, the mean of this sampling distribution would be centered at 31 hours. And so it would actually look like this. This is the reality or the real sampling distribution, right? So keeping this in mind, the black is what we're theorizing, and the red is what actually is. The power of the test is going to increase when the sample size n gets bigger. And here's why. Remember, the power of the test is essentially rejecting HO when a certain HA value is actually true. So going back to my picture, if this red HA value is actually true, okay, and I have this certain sample size in my black sampling distribution, right? If I increase my sample size, remember we said that decreases sampling variability. So my theorized, like what I'm assuming, my sampling distribution would actually get like skinnier, right? And so I would have kind of like less tail area here and less overlap with my black theorized distribution versus my red distribution that is reality. So what happens here? One of my X bars, I think it's gonna occur according to this black curve, the second black curve that I drew, right? The skinnier black curve, because we're talking about increasing our sample size, right? And let's say that alpha is, 0.05, that little rejection region, that black rejection region that I drew there. But in reality, when I actually go out and sample, my X bars are going to be centered over here around this 31 value. So in other words, my X bars are going to be kind of further away from the majority of the X bar values that I think I'm going to get. So I'm going to be more likely to reject HO. So essentially, the power of the test is going to increase at a certain population parameter value when I increase my sample size. Okay, another way to increase the power of a test is to increase my alpha level. So in other words, let me draw this quick picture again. So if this is my number line, 29, 30, 31, 32, right? These are all X bar values. So my sampling distribution, I'm assuming it's this black one, but when in reality, it's this red one, right? If my alpha value was 0.05, then theoretically, anytime I'm in this top 5% region of that black hypothesized sampling distribution, I would reject HO. And remember, power is when we reject HO. Well, if I increase my alpha to, let's say, like 0.10, 10%, that means my rejection region is getting bigger. And so therefore, my power would increase as well. Okay, and then finally, the null and alternative parameter values are further apart. So again, with my picture, think of this as a number line of all possible like X bar values. Same, HO, mu is 30, HA, mu is, greater than 30. So this is my hypothesized sampling distribution, right? Centered around 30. So the mean of all the X bars would be 30. That's what I'm hypothesizing. That's what I'm assuming to be true. Well, if my alternative parameter value was 31, kind of like what we've been talking about, the sampling distribution would actually be here in red, right? And so, again, think about this rejection region. Let's say alpha is 5%. I would reject any X bars over here past this whatever that value is. But in reality, I could get like red X bar values down here, right? And so therefore I wouldn't be rejecting HO. On the other hand, if my actual alternative parameter value, instead of saying, oh, I think it's like, or instead of saying the actual parameter value is 31, let's pretend the actual population parameter value, so population mean, was 32. Then, instead of the red distribution here being my actual sampling distribution, it would be centered at 32. So the question is, how many of the values, remember, we would not be rejecting HO if my X bar is to the left of that black line. How many green X bar values would be to the left of that black line? Either none or very, very little compared to the red ones. So the further the hypothesized value and the actual value are, the greater the power is. Okay, now I know that some of these might sound a little bit confusing, the reasoning behind these. You don't necessarily need to know how it works. I just explained to you how each of these 3 bullets work. You don't need to know necessarily how they work. You just need to know that that's what happens, okay? So here's an example of a question that you might be asked. Take a minute and read this. Okay. So the hypothesized value is 10%. The alpha level is 5%, right? The sample size is 300. And we're saying the power of the test at this population parameter value. So in other words, if if HA actually was true. So HA is that the actual population proportion of patients who experience nausea is actually less than 10%. I know it's 8%, right? The power of the test to detect or to find like statistically significant evidence is 29%, right? So questions A, B, and C. If we make these changes, does that increase the power of the test or decrease the power of the test? All right, so if we, and they tell us, where do they tell us? Oh yeah, I'm sorry, they tell us that alpha is 0.05 to begin with. So alpha is 0.05. So if I use alpha is 0.01 instead of alpha of 0.05, so in other words, if I decrease alpha, that's also going to decrease the power of the test because it makes it harder to reject HO. So now, remember the hypothesized here, your HO was P is equal to 10%, HA was P is less than 10%. And we said the power of the test initially was for a given population proportion of 8%. Well, now it's the actual population proportion was 6%. That's further away from 10%, right? So that's going to increase the power of the test because, excuse me, the true population proportion is further away from that hypothesized proportion, which was 10%, right? And I'll put that up here again. So your HO was 10%. So 6% is further away from 10% than 8% is. So we're going to increase the power. And then finally, our initial sample size was 300, right? If we decrease the sample size, that decreasing of the sample size increases sampling variability, right? Our our hypothetical sampling variability. And so therefore, I'm decreasing the power. In other words, it's going to be like less likely that I make the right decision and reject HO. All right. So hopefully that was helpful. And again, these are the type of questions that you should be able to answer about power, in addition to kind of interpreting what does power actually mean in each given situation. Thanks for watching.